Hi everyone, Miss Fung here. I hope you are doing well. Today we're talking about rational exponents. This comes from our section 7.3 of the textbook, and believe it or not, is the last lesson of the year. How very exciting. So why don't we dive right in? We're going to start with a definition. Now we're ultimately going to have kind of two definitions of what rational exponents are, but ultimately it comes down to the name. We're looking at exponential equations or expressions where those exponents are ratios. It's in the word. So that could mean they are fractions. The sort of simpler way of looking at these, or one of the simplified ways of looking at this, is if we've got x to the 1 over n power. Now, I often write my rational exponents kind of sideways like this, just so it's more obvious to me that both the 1 and the n are part of the exponent. So if we have this, our base is x and our exponent is this expression 1 over n. Then the equivalent radical form of this expression is equal to, I might read this as the nth root of x. So notice our base of the exponent becomes our radicand, that value underneath the radical sign. The denominator of the exponent, that becomes the index on our radical, or the index on our root. Now we are specifying that we're only talking about positive values of n. N has to be positive here. The other clarification is that we're talking about only positive or 0, I guess, values for the base x if n is even. So that means if we're talking about, let's see, just a plain square root of x, or like the 4th root of x, so on and so forth, we're only talking about x being a positive value there or being equal to 0. Otherwise, for example, if we take the square root of like -2, that's imaginary. And right now we're kind of clarifying that we're only really dealing with real numbers. We're kind of eliminating imaginary values from our world at the moment. Okay, so that's kind of our basis of our definition for rational exponents. Now, the same rules, the same properties of exponents apply to rational exponents as well, like we might imagine. So what does that really look like? Well, let's look at our example. We've got a to the 2/3 times a to the 4/3. So the same base, and we're multiplying them together. So what that means is we end up adding together the exponents. So this will look like a to the 2/3 plus 4/3, which of course that can be simplified. We've got common denominators for those two fractions. So that's a to the 6/3, and that simplifies to a squared. Okay. So let's see, in the definition, we talked about, for example, a to maybe the 1/3. X to the 1 over n is what we're looking at. So how do we deal with this 2/3 then? Where does the 2 go? So that's what I mean by us having kind of another definition. Here's our first one, where the numerator on our fraction in the exponent place is just 1. But, of course, that numerator can be other values. So here's our second definition. If we've got some x to the m, like Mary, over n, like Nancy, power. So that could also look like x to the m over n, like that. So that could be turned into radical form in two different ways. Now our denominator of the exponent still becomes the index on the root, so we're still taking the nth root. However, the numerator, m, we see that showing up as the exponent still on the radicand, or in the second radical form here, actually the exponent on the entire expression. So the exponent can indeed be underneath the radical sign like we have at first, and it can be outside the radical sign. Those are equivalent. So you kind of might be wondering where this comes from. And I want to go back to my x to the m over n power here. So I'm just going to look at m over n for a second. Another way of maybe representing m over n is m times 1 over n. Now that 1 over n, that should look like the initial kind of exponent we talked about. So I could rewrite perhaps x to the m over n as x to the 1 over n times m, or perhaps x to the 1 over n all to the mth. It's kind of hard to talk about. But that's essentially where this comes from. We're taking our x to the 1 over n and using that first definition, we can turn that into the nth root of x, and then we still have our exponent m hanging out on the outside. So that's kind of a breakdown of where that comes from. Let's give that just a little bit of practice. Let's go from exponential form, which is what we have in both of these expressions, and let's rewrite them in radical form. So that means taking our denominator of the exponent, 5 in this case, and turning that into the index on our root, index on our radical. We take our base and we make that the radicand, the number underneath the radical. And we take the numerator from our, I wanted that to be a different color. We take our numerator from the exponent, and again, that can go underneath the radical sign, but another equivalent way to write this would be 5th root of x all squared. So maybe take a second to turn x to the 5/3 power into radical form. Could be two answers there. We again are going to take our base and turn it into the radicand, but now we're talking about the cube root. So we'll have the cube root of x to the 5th or cube root of x all to the 5th power. Okay, so when we are dealing with sort of converting between exponential to radical form, then we try to represent variables that are part of the same term. That is, they're not separated out by like addition and subtraction. So if they're variables that are in the same term, they're multiplied together, we try to get them underneath the same radical sign or a single root. So what that means is we want to convert the variable so that they have the same root index, the same number in front of the radical sign. Now, in order to do that, our goal is going to be getting a common denominator in those exponential, in those rational exponents. So in our first example, we have x to the 1/2 and y to the 1/3. So our task is to come up with a common denominator between 1/2 and 1/3. And hopefully we're seeing that that lowest common denominator, the LCD, would be 6. So one way to rewrite this expression is to change x to the 1/2. Let's change it into x to the 3/6. All right, that's equivalent. And y to the 1/3 we can say is y to the 2/6. Okay, now there's kind of two maybe trains of thought. We can then turn each of these separate variables into radical form themselves. So I can rewrite x to the 3/6 power as the 6th root of x cubed. And I can also rewrite y to the 2/6 power as the 6th root of y squared. Okay, once we have our same root index, that is the same number in front of the radical, I can kind of combine these. So I can rewrite this as the 6th root of x cubed times y squared. Okay, so that's one way of getting to perhaps the simplified version of our radical form. Another way, though, is if we go back up to now having common denominators in our exponents, we can actually rewrite this as x cubed times y squared, all raised to the 1/6 power. This is almost undoing our power of a power property of exponents. Remember, we are essentially like undistributing the denominator here. So written like this, we can just go ahead and convert this into radical form, taking that 1/6 and turning it into the 6th root of, and then what's left here, x cubed, y squared. Okay, so either way we get to the same kind of answer. Same idea over here with our second example. We've got a to the 6/5, b to the 2/5. So perhaps I'll show this just one way. I'm just going to rewrite this as a to the 6th times b squared, all to the 1/5 power. Okay, so to the 1/5, that's the same thing as the 5th root. So the 5th root of a to the 6th b squared. We may be tempted to just call it good here, but this is actually not simplified. The reason I know I can still kind of keep going is because there's an exponent underneath my radical sign that is larger than the index. Whenever that's the case, I can keep simplifying. So I'm actually going to break apart a to the 6th. I'm going to break that into a to the 5th times a. My b squared, I'm not really going to be able to do much with that. But I'm taking the 5th root still of all of this. But 5th root of a to the 5th, those are essentially inverse operations. They undo each other. So we're just going to have an a now on the outside of our radical sign. So we'll have the absolute value of a to ensure it's positive, times the 5th root of plain old a times b squared. Now that would be our fully simplified answer. Okay, let's look at a complicated example. So to give yourself some space for this problem, we're going to go kind of carefully through this and show all of our work. I want you to try to do this in your own homework as well. Show your work very carefully in kind of a linear fashion as well. Okay, so we have a complicated expression that we want to simplify. Now, I will also add that I am going to be putting our final answer in radical form. Okay, so with expressions like these, where we've got lots of exponents, we've got some negatives, we got some things to simplify, we have an exponent on the outside of the entire thing, there is really a variety of first steps that you could take. There's a whole lot of things you could do first. I personally like to kind of start with the negative exponent that's on the outside. Because it's negative, I'm going to take the reciprocal. I'm going to write this down. Take reciprocal first. Now again, this is just one of the many first steps that are possible in a problem like this. So I'm going to be very careful and label this as my step 1. So the reciprocal, of course, means flipping this ratio completely upside down. So our new numerator is 2 times x to the negative 1/3 power times y, all over 12 times x to the 2/3 power times y to the 1/2 power. And this is all being raised to not the negative 1/3, but now the positive 1/3 power. Okay, so that's kind of one approach you could take with your first step. The rest of the steps are kind of similar. You could sort of go in several directions at this point. What I'm going to do is maybe deal with my remaining negative exponent. Notice in this numerator, I still have a negative 1/3 on my x. So by dealing with that, I mean I'm going to actually move it to the denominator and make the exponent positive. So for my second step, what's left there in the numerator? Still a 2y. And then in the denominator, I still have a 12. I still have this x to the 2/3. Now I also have an x to the positive 1/3. And I still have y to the 1/2. Okay, and that is all still being raised to the 1/3 power. Okay, so I don't have any more negative exponents to deal with. That's kind of nice. What else can I do here? Well, I've got a 2 and a 12. That simplifies to just leaving a 6 in the denominator. I also have an x to the 2/3 times an x to the 1/3. Remember, that's the same thing as adding our exponents, which is going to be equal to x to the 3/3, or just plain old x. Okay, so I might start kind of adding what I've got here. I know I have a 6 in the denominator from my third step, and I have an x. What about these y's, my remaining like bases? I've got a y, we could say to the first power in the numerator, and a y to the 1/2 power in the denominator. So perhaps I will rewrite this as y, well, it's y to the first, so that's also y to the 2/2 power for getting a common denominator, minus y to the 1/2 power. Okay, well that's going to be equal to y to the 1/2 power. So let's see, I guess I'm left with a y to the 1/2 power in that numerator. Now this is all still being raised to that 1/3 power. So we still have fractions in our exponents to deal with here. Okay, I think that's probably what I'll do next, is kind of deal with those fractional exponents. That is, take this one that's on the outside, 1/3, and essentially distribute it. It's a power of a power. That's the name of our property here that applies. So it's applied to the y to the 1/2, it applies to the 6, and it applies to the x. So let's just rewrite that for now. I know I have y to the 1/2 to the 1/3. That means those exponents are being multiplied together. I have 6 to the 1/3 power, and I have x to the 1/3 power. Okay. So I'm going to ask you to remember a syntax rule of mathematics. That syntax rule is that I can't have a radical in the denominator. We simply say, sort of as mathematicians, that this is something we don't allow. This is not fully simplified. So we have to do a process called rationalizing in order to get those out of the denominator. That is going to be true whenever we have rational exponents in the denominator as well. For example, let's take our x to the 1/3 power, and remember that that's the same thing as the cube root of x. So really, a rational exponent is a radical. Therefore, rational exponents can't be left in the denominator and it be considered simplified. So we got to rationalize this, meaning I need to multiply by something that makes my denominator no longer equal, or no longer having these rational exponents. So what I'm going to multiply by, I'll write this step 5 up here, I'm going to multiply my denominator by 6 to the 2/3 power and x to the 2/3 power. So this is what I'm multiplying the denominator by, which is already 6 to the 1/3 and x to the 1/3. Now, why did I choose that value? Where did that come from? Well, I just want to point out that 6 to the 2/3 power times 6 to the 1/3 power, remember this was already in the denominator. If we add together those exponents, we'll get 6 to the 3/3 power, or 6 to the 1st, which is just plain old 6. So if I multiply by 6 to the 2/3, all of a sudden I don't have that rational exponent. Same idea with x. X to the 2/3 times x to the 1/3, we're just going to get plain old x. So that's what we're kind of aiming to do. Picking fractions as exponents that will help us get rid of those rational exponents. Now, of course, I can't just multiply the denominator by something and then not do anything with the numerator. I have to keep these things equal. So I'm going to be multiplying by, quote unquote, 1, something divided by itself. So I'm multiplying both the numerator and the denominator by the same thing. Now, what exactly is that numerator? That numerator is y to the 1/2 times y to the 1/2 times 1/3. That's the same thing as y to the 1/6. Again, we're multiplying those exponents together. So we get y to the 1/6. Okay, so let's multiply all that business together so that we will have, in our numerator, I'm just multiplying straight across. So I'll do 6 to the 2/3, x to the 2/3, y to the 1/6. And then, like we said, those the denominators, as designed, we no longer actually have to deal with any rational exponents. We just have 6x. Okay, we're almost there. There's still some craziness going on in the numerator now. Like we said kind of earlier, we want to try to represent these as being underneath the same radical. So we're going to be looking for common denominators between our rational exponents right now. And it looks like, because we've got a 3, and a 6, that common denominator is just going to be 6. So let's maybe take a step to rewrite that. We'll have 6 to the 4/6 power. We'll have x to the 4/6 power and y still to the 1/6 power. It's still all over 6x. Okay, so let's finally turn this into radical form. Let's see. We're going to have the 6th root of 6 to the 4th times x to the 4th times just plain old y. We could write like y to the 1st, but really that's extraneous. And our denominator is still just 6x. Okay, so I would say honestly, we could leave this here. We're good. 6 to the 4th isn't technically simplified. I kind of want to actually figure out what that number is. But unless you have a calculator, I would say just leave that where it is. If you do have a calculator, let's actually determine what is 6 times 6 times 6 times 6. And we should get, because I plugged this in earlier, we should get the 6th root of 1296 times x to the 4th times y all over 6x. Okay, that is our simplified and rationalized form. All right. Let's see. There we go. Okay. So sometimes it is going to be easier to convert something that's already in radical form, convert it into exponential, and then use some exponent rules to try to simplify things. So let's look at an example here. Now this doesn't necessarily have to be converted into exponential form, but it can be. So what that means is taking each piece, so my square root here, I'm going to turn this into exponential form. Remember, this really is the square root. We don't bother usually writing the index for the square root since it's our default, but there is kind of an invisible 2 there. So the exponential form of this would be x squared times y all to the 1/2 power. Now the other piece would be x cubed times y all to the 1/3 power. Okay, so we've got a power of a product situation going on here, again, where we want to essentially distribute our exponent into the parentheses. So that's going to look like x to the 2/2 power, y to the 1/2 power, x to the 3/3 power, and y to the 1/3 power. Notice my parentheses just kind of went away. Because this is all multiplication at this point, we don't really need those extra parentheses. In fact, the order here of all of our separate factors can be rearranged and it's still the same. I might point out that x to the 2/2 power, that's just x. Same with x to the 3/3. So really, I'm going to end up with an x squared, x times x. What about my y to the 1/2 and my y to the 1/3? Well, let's find common denominators. We can represent that as maybe y to the 3/6 times y to the 2/6. Again, when we've got those like bases, we want to add together the exponents. So we'll end up with x squared times y to the 5/6. Okay, well, we started with radical form, so I'm thinking we probably should go ahead and put this back in to radical form. So the only thing we need to adjust is this rational exponent piece. We'll still have an x squared, but then we'll be multiplying by the 6th root of y to the 5th, or of course, 6th root of y all to the 5th. Okay. So what about decimals as exponents? Technically, those are rational as well. They're just written in a different form. However, we don't generally consider decimal exponents to be fully simplified. So I do want to continue kind of working with this. I've got like bases. I've got a consistent base of x going on here. So that means maybe if I focus on the numerator, I need to add those exponents together. X to the 1.2 plus 0.4. And we're still dividing by x to the 0.2. So let's see, that's going to look like x to the 1.6 over x to the 0.2. Okay, well, I've got like bases that are being divided. So that means I subtract my exponents. So this looks like x to the 1.6 minus 0.2, or x to the 1.4. Okay, so this is simplified a little bit. It's not fully simplified though. I still want to get rid of the decimals. So what I can do is actually break this apart. There's maybe two ways to think about this, so I'll show one of them maybe in red here, and then I'll show the other way. 1.4. Another way of writing 1.4 is 14/10. So really, I can say x to the 1.4 power is the same thing as x to the 14/10 power. Well, 14/10, that simplifies. That simplifies to 7/5. That's just dividing both the numerator and the denominator by 2 there. So I can then kind of turn this into my radical form, 5th root of x to the 7th. Now here I want us to recall back to earlier where I said anytime we've got our exponent that's larger than the index, we need to keep simplifying. So I'm actually going to break apart my x to the 7th. I've got all kinds of background noise today, I'm sorry. I'll let that guy pass. All right, there we go. I'm going to break my x to the 7th into x to the 5th times x squared. If we're taking the 5th root of all that, that of course means my 1/5 root of x to the 5th, those are those inverse operations. So we just get our plain old absolute value of x. We still have our 5th root of x squared. Okay, so that's one way to think about that. Now the others may be a little bit more straightforward. It's recognizing that x to the 1.4 power is the same thing as x to the 1 plus 0.4 power, which is like x times x to the first times x to the 0.4 power. Okay, but 0.4 as a fraction is, we said earlier, 4/10, but that's also 2/5. 4/10 simplifies to 2/5. So I can break this now into that radical form, and I'll end up with, let's just go this way with it, my, again, absolute value of x times the 5th root of x squared. So same answer. So here I've got a few maybe challenging problems where, similar to the longer example we did, there could be several first steps. Don't worry that there's like one step that you should be looking to always do with expressions like this. It's more like kind of a puzzle, putting together all of the different properties of exponents, dealing with radical form, and all that good stuff. So my recommendation is to pause and write all these down and work on solving them. I'm going to count down from 5 and then show the answers. So go ahead and pause now. And in 5, I'll show the answers. Okay, there we go. Please let me or whoever your geometry teacher is know if you've got any questions there. Otherwise, thank you so much for tuning in. I hope you have a great day. Bye.